For decades, we've been hearing that composite materials are basically a miracle for aviation. Lighter, stronger, more fuel-efficient planes, all thanks to this black aluminum. But you know what? That's really only half the story. The truth is, these benefits come with a whole hidden set of trade-offs, and they're complex, they're costly, and they're absolutely crucial to understand. I mean, look, on paper, the case for composites is a slam dunk. You're talking about a material that's way stronger than traditional aluminum while being about 1.5 times lighter. Plus, it doesn't corrode. This was the big sales pitch, right? A total revolution in airframe design that was supposed to lead to lower maintenance costs and a much longer service life.
But here's the twist. As Aviation Consumer points out, the real-world experience has been, well, a lot more complicated. The industry learned pretty quickly that by solving the old problems of metal, corrosion and fatigue, they'd accidentally created a whole new set of challenges. And these new ones, they're way harder to see and a lot more expensive to fix. And that first major challenge starts with something that's kind of unsettling, to be honest. Damage that is fundamentally invisible to the naked eye. This is a complete 180 from the world of metal aircraft. This right here captures the core of the problem perfectly. Think about it. If a baggage cart smacks into an aluminum fuselage, it leaves a big, obvious dent. You can see the damage. But with composites, they can take the same hit, spring right back into shape, and show little or even no mark at all on the surface, all while the internal structure is just completely wrecked. So what is this hidden damage we're talking about? Well, it's stuff like delamination, where the layers of the material get peeled apart from the inside. Or fiber breakage, where the actual carbon fibers that give it all its strength are just snapped. See, unlike a metal crack that grows slowly over time, this kind of internal damage can lead to a sudden, catastrophic loss of strength. This whole phenomenon is so well known that it actually has a name, barely visible impact damage, or BVID. In fact, regulators like the FAA require that a composite structure has to be designed to handle its absolute maximum stress load, even with a certain amount of this hidden BVID already present. That's how serious and common this issue really is. And it's not just impacts we have to worry about. There's another invisible threat: moisture. A lot of these parts use a honeycomb structure inside to add stiffness without adding weight. But the problem is, these are really vulnerable to water getting inside through tiny cracks or bad seals, and that trapped moisture can then just quietly go to work degrading the adhesive and weakening the part from the inside out. So, okay, finding the damage is super difficult and needs special equipment. But what happens when you do find it? Well, that leads us right into the second major trade-off, the incredible challenge of actually repairing it. Because like the saying goes, you can't just rivet a patch on it. A standard structural repair for composites is called a bonded scarf repair, and honestly, it's more like surgery than mechanics. A technician has to painstakingly grind away the damaged material, creating this perfectly angled taper. Then they lay in new sheets of composite, making sure every single fiber is lined up exactly the way it was originally. And finally, they have to apply heat and pressure to cure the whole thing, turning it back into a solid part. And that last step, the curing, is unbelievably tricky to do outside of a factory. See, when you put a heater blanket on it, the thicker parts of the structure might not get hot enough, which gives you an undercure and a weak bond. But at the same time, the thin parts can get too hot, causing an overheat that actually damages the material. It's an insane balancing act. The difficulty of getting this right has led to a really critical safety rule: bonded repair size limits. Agencies like EASA actually require that the aircraft has to be able to withstand critical flight loads even if the entire bonded repair fails. That is a huge admission that detecting a bad bond is so hard, you just have to assume it might fail. So what's the bottom line? Well, all of this complexity, all the specialized training, and all the expensive equipment means that composite repairs are just way, way more expensive than what you'd see with metal. The time and money it takes to get a damaged composite aircraft back in the air is one of its biggest life cycle realities. Which brings us to our third major trade-off. We've built this amazing airframe out of what is essentially an electrical insulator, a type of plastic. So what happens when that structure gets hit by a lightning bolt, carrying up to 200,000 amps of current? Let this number sink in for a second. Carbon fiber is about 1,000 times more resistive to electricity than aluminum. A middle plane, it acts like a Faraday cage, right? The current just flows harmlessly over the skin. A composite airframe, though, it has no natural path for all that energy to go. So without protection, the results are, well, catastrophic.
The resin can flash into gas, literally blowing the composite layers apart from the inside. The current can arc across metal fasteners, creating sparks right next to fuel systems. And the massive electromagnetic field can fry the plane's wiring and avionics.
As research from places like NASA shows, solving this problem was a massive engineering challenge. It meant completely rethinking how you make an airframe electrically safe in the first place.
And the solution, ironically enough, was to add metal back into the structure. Yep, engineers embed a fine metallic mesh or foil right into the outer layer of the composite skin. They connect all the different panels with metal bonding strips and use special fasteners, all to create one unbroken conductive path for the lightning, basically building an artificial metal skin.
And this quote from Dr. Yulia Kostogorova-Bilar really just hits the nail on the head. To solve the lightning problem, you have to add weight back to the aircraft. And that, of course, partly cancels out the #1 reason you wanted to use lightweight composites in the first place.
So when you pull all of this together, the invisible damage, the super complex repairs, the need for lightning protection, you really start to see the true cost of the performance gains that composites offer. The trade-offs are crystal clear. The promise was resisting damage, but the reality is hidden internal damage. The hope was for simple repairs, but that was replaced by complex, costly, and heavily regulated procedures. And the big benefit of a lightweight structure, that was compromised by having to add metal back in for electrical safety. And let's be clear, this isn't some minor thing. A NASA report on lessons learned puts it very plainly. Costs are the single biggest problem. And that means the entire life cycle, from manufacturing to inspection to maintenance and repair, it's all more expensive than for metal.
It all comes down to a core principle, a truth you see everywhere in aerospace engineering. There is no such thing as a free lunch. Whenever you push the boundaries of performance with new materials, you will always introduce new and often unforeseen consequences for maintenance and long-term support.
So in the end, this isn't about saying composites are bad. They're not. They've enabled a whole new generation of incredibly efficient aircraft. The real takeaway is that they are fundamentally different. They aren't just a drop-in replacement for aluminum. They're a completely new technology that demands a whole new philosophy of how we inspect, maintain, and repair aircraft.
And this really leaves us with a critical question for the future of aviation. As we keep innovating, chasing performance with even more advanced materials, how are we going to balance those gains against the ever-increasing complexity and cost of making sure these aircraft stay safe for their entire service life?